In this video, I'm going to talk about using ftest to compare nested models. So the setting for this video is that we have a full model that makes, where we can get estimates from the full model that are based on our estimates of an intercept plus our estimate for the coefficient on one variable plus our estimate for the coefficient on another variable and the coefficient on a third variable. This model will give us sums of square error for the full model, which we compute by looking at the individual errors between each observation in our model's prediction squared and summing those up. This model also has a certain number of parameters, which in this case is 4 for the 4 different coefficients that are being estimated. And we have a reduced model which gives us estimates from our reduced model based on estimating an intercept term plus a coefficient on just one of those variables above. This will also give us a sums of square error for this reduced model, which can be computed in a similar way, where we look at the individual errors based on predictions from this model, square those and add those up. And this model also has a certain number of parameters, which in this case is 2 for the intercept and slope. And in this setting, we're interested in testing the null hypothesis, which is that all of the parameters in the full model that are not in the reduced model are equal to 0. And it would be the same type of test or the same general type of setting even if the number of parameters that we're interested in testing is just 1. Yeah, so what we do to test this hypothesis is we can construct an obtained F statistic, which is we compare the sum squared error from the reduced model against the sum squared error for the full model. So we're looking at how much the sum squared error is reduced by adding those 2 parameters relative to the number of additional parameters that we're adding in the model, which would be PF minus PR, so the difference in the number of parameters, over the sum squared error from the full model relative to the degrees of freedom of that model, which are the number of observations minus the number of parameters in that model. And that will get us an F statistic, which comes from an F distribution with numerator degrees of freedom that are the difference between the number of parameters in the full model and the number of parameters in the reduced model. Denominator degrees of freedom that are based on the degrees of freedom for the full model. And to make a decision about rejecting or failing to reject, we would compare the obtained value that we get to an F distribution where we specified some alpha, which is the probability of getting this obtained F value if the null hypothesis were true, which is the same as saying if those parameters that we're interested in testing are all 0. Specifying this alpha determines a critical F statistic, which we then compare the obtained value to decide whether or not we reject or fail to reject the null hypothesis. In this case, if the obtained value is greater than the critical value, then we would reject. And And the interpretation of that would be that there's sufficient evidence that at least one of the parameters that we were interested in testing is not zero. A major limitation of a test like this is that it doesn't really tell us which parameter might be non-zero. And in other videos, I compare this with other types of hypothesis testing, which would give more information about which parameter is non-zero.